You have a question?
Yeah, I have a question. Does this cellular automata have Hilbert space structure built in?
Not by itself. It is a cellular automaton made by, you can make it by a computer. You can take a computer, you can instruct the computer what to do. You can program the computer. Is there Hilbert space in the computer? No, there's no Hilbert space in the computer. There's only a computer program in the computer. Similarly, in a cellular automaton, the only thing it is there is the computer that does the computation, not Hilbert space. But I'm free to introduce Hilbert space because it helps a lot. It helps me to do a perturbation expansion, which brings me the answer much, much faster than trying to compute for every probability what happens, because I'll never get the answer. It's too complicated. So, yes, but then there's still a question. Oh yes, the statement now is I can perform now the 1/L expansion. And that is a genuine expansion, but it only makes sense if L is an integer. Because I was working with integers all the time. I cannot work with fractional numbers, not unless they're rational, then I can replace the rational numbers by integer numbers according to some prescription. But I cannot work with arbitrary real numbers in this theory. So the values of 1/L are rational. And this means that the coefficients that come with these interaction Hamiltonians are rational coefficients. Those rational coefficients tell me that in the standard model, these coefficients are the constants of nature, like the fine structure constant, 1/137. So in a standard model, I don't know what the number is. I can replace it by any real number I like and do the perturbation expansion. Same thing here. I can replace 1/L by any number I like and do the perturbation expansion. But physically, you should expect the 1/L to be a rational number. L is an integer, and I can put some integer on top as well. So I can make this a rational number. But the rational number should be believed. The non-rational number should not be believed, as if someone has not done his job right yet. Because if this number is not rational, with a real number like pi, then I still have an infinite number of decimal places to solve before I can calculate anything. That's not a deterministic theory. So if L is not integer or rational, I don't have a deterministic theory. If I assume to have a deterministic theory, I can eventually expect that this theory will give me a prediction for the find such a constant. I say this very carefully because no, I cannot compute to find such a constant. I'm not even close to that. So, but I can just state right now that all the constants, all these more than 20 constants of the standard model, they're all rational numbers, which in principle should be computable. But unfortunately, I haven't computed them because there is a very big hole. Here comes, this is the final transparency practically. This is transparency saying that there's one thing that the standard model has and the model I've written down does not. And that is symmetries. There are many, many symmetries in the standard model that occur, such as translation symmetry. Now, translation symmetry on the letter is relatively easy. You can look at the eigenvalues and then you can make continuous translations on the letters. That's relatively easy. But make continuous rotations on the letters is actually very hard in practice. Lorentz transformations are even more difficult because the Lorentz group is a non-compact group. So to make a theory Lorentz invariant, you have to make infinitely many tests to see whether the theory really is Lorentz invariant. So that's very, very hard to comply with. So Lorentz invariance is very difficult. Local gauge theories, the standard model is characterized by having a local gauge invariance in the definition of your fields. So I should introduce local gauge invariance in the procedure I've done so now. I have not been able to do that. So this is where I fail to get the final theory. I don't know how to make the theory locally invariant. Well, I can replace the local gauge group by a discrete gauge group, a permutation group, which has a discrete finite number of elements. Then you can do such a thing on the lattice. But the continuous gauge theories are then very difficult to make. The Brout-Higgs mechanism on the lattice, well, that's also a symmetry procedure. And the holy grail really is a general coordinate transformations. I want the theory eventually also to comply with general relativity. It doesn't at this stage. So that is where I failed. I haven't been able to make the theory that powerful, but I think this is a good start that I've made. And this would be a good way to formulate the theory. Now the hard work still has to be done. And that is answer these questions about these symmetries that I had here before, and find a systematic way to translate all the properties of the standard model, including all the mathematical difficulties, properties of these symmetry groups, how they interact mutually to get the states of the standard model. Very interesting question. The standard model gives you all the answers in terms of the standard model language. To turn that into a quantum language, I told you how to do that in principle. In practice, that will be extremely hard, but I'm sure that there will be some smart young people coming up. I'm too old now to do this calculation in all detail, but maybe young people will be able to do this and figure out how to translate these words into practical calculations. And here I want to thank you.
But as we know, there is no a pure vacuum. There are virtual particles which appear and disappear every second. From this point of view, how can we talk about determinicity even for a single electron if it is bombarded every second by virtual particles?
Well, I think you know what a van der Waals gas is. A van der Waals gas is a description of a gas in classical terms. It has the equations are that the atoms are assumed to be billiard balls. Well, they aren't just billiard balls, but suppose two billiard balls come together, they hit each other, and the way they bounce depends on the way they touch each other, and they can touch each other in infinitely many different ways. So if you follow a van der Waals gas closely, you can write down the equations for how the balls will hit each other, and you can assume a stochastic behavior. That is to say, when two balls approach each other, you never know exactly how they will approach each other. Maybe you know it with some very limited precision because you know where the balls came from, but you can do that calculation in principle. There's no quantum mechanics there, but there's also no complete determinism in the sense that you have to introduce stochasticity because you don't know where these balls are exactly. It's too complicated. They form a random distribution in this world. But there's no quantum mechanics in the van der Waals gas. So that theory, for that reason, doesn't work so well. But it could have worked much better if people wrote down a much more powerful random noise model for the van der Waals gas. Maybe they can get an approximation of reality there much more precisely. But there's no reason to say I exclude the van der Waals gas because it doesn't predict things. No, it predicts things fine. It just isn't the right theory. So
maybe on this way we can construct an alternative theory which will be to a certain extent equivalent to current quantum mechanics theory.
Absolutely, that's right now that's a conjecture. I cannot prove it. I don't even know how to do it. So I cannot prove that that one can make a classical theory that produces exactly the standard model, because the standard model has features that I find very difficult to reproduce. That's only because I have my own mathematical limitations. But I think in principle, a very smart person could figure out all these things part by part. So you first have to understand how can a model be translation invariant, then you have to understand how can a model be rotation invariant, and yet have finite amount of information like in a cellular automaton. I think that it's possible, but it's very hard to reproduce rotation invariance. Then Lorenz invariance and other symmetries are even harder to reproduce. So that's all the work you still have to do. But in principle, I think these questions have nothing to do with the fundamental question, which is whether stochastic behavior can come out. So I think that question can be answered theoretically by saying no matter what models you put in your cellular automaton, you'll get behavior that will generate effectively random walks, so that a random behavior, so that we are in a good position to start from here. But we still have to do all the hard work to get it done precisely.
Okay, thank you.
More questions? Yes, please.
Yes, I still can't get how your theory can overcome Bell's inequality. Do you mean Alice and Bob cannot choose the axis of experimental device by free will. They can't choose device axis of device randomly.
Well, I explained that you have to ask this question at the level of the classical underlying theory. So how can the classical underlying theory violate Bell's inequalities? Well, the classical underlying theory does reproduce exactly the events that Bob and Alice are measuring. But there's one thing that the classical theory cannot do, which is it cannot force Bob and Alice to do what we call a counterfactual measurement. So to do a measurement, you have their devices in certain angles, and they see a photon going through this filter, not going through that filter. So then they make a note of the measurements, but the outcome of the measurements is yes, the photon went through, or no, the photon did not go through. So ik kan een beetje zacht zijn. So the photon can either go through or cannot go through. They cannot put their devices such that the photons will be superpositions when they go through those states. That is impossible. And that is incorrectly assumed in these arguments about Bell's inequality, that you can put the device into a state where the photon will come out with certain probabilities. No, photons will only either come out or not come out in all circumstances, which means that the real universe is always in an ontological state. This is so-called ontology conservation law. The universe starts off in a state that, yes, the balls are here and not there. It will always be in a state where all these balls, billions of them, are all in definite positions, and they are not in other positions. I cannot put them in any other position. So the decision made by Bob and Alice to make a certain configuration of their settings was a decision made in their minds eventually, and in their minds they could make a choice, but they could not make a superposition of choices. How can I can ask you, can you make a choice that your actions or your questions are a superposition of two different questions? No, you cannot. You can only ask this question or that question. You cannot make a superposition. So that error was being made by Bell, and from his point of view, it was difficult to see why you should not make that assumption. But my claim is yes, you can you can say that is forbidden. Bell was not allowed to ask Bob or Alice to make a superposition of the settings of their measuring device. Impossible. They cannot.
Okay.
And the reason why they cannot is because in their past, it couldn't, the switch could not be made. And Bell said, well, who cares what was done in the past? And then Bob and Alice made decisions independent of the past. No, they did not. Their decision is linked to what happened in the past, whether you like it or not. So that is the lack of fundamental free will that Bob and Alice have.